Hello. Today I will discuss Lab 2, in which we predicted the motion of a falling object. The purpose of this lab was to examine Newton's second law, the momentum principle, in action, in which I would observe the motion of a falling object and compare my observed motion with two computational models based on physics principles. Here's a video of my observed motion. I dropped a balled up plastic bag. I attempted to drop it straight down, but because it did not, we must consider that there could be some error within my data. Here you can see my tracker data in which I use the program tracker to map the position over time of my object, specifically in the y direction. It's important to note that the ball started from rest and had started from rest with a 0 initial velocity, and the duration of the fall was 0.633 seconds. Let's look at Newton's second law. Using the velocity update formula and the fact that we know that the change in velocity is not 0, we also know that the net force is not equal to 0. So there must be at least one interaction between the object and its surroundings. What interactions do we know happen with falling objects? We know of weight force, in which the Earth exerts a weight force on objects that are falling. So let's use the fact that net force could equal negative mg, which is the weight force. For my computation model, using only the weight force, I inputted the necessary conditions, including value of g, the direction, and the value of b, which only applies to drag force, so it is equal to 0 in this model. I inputted my time and the formula negative mg, which is the weight force, using the coding values, and updated the object's velocity and position. From the tracker data, you can run my own code from the description below, but using the data from my computation model and my observed model, I created this position versus time graph in which we can see that the computational model underpredicted the actual observed motion collected in data in tracker. Let's look at Newton's second law again. So what is an additional force that could be applied to the ball? Well, drag force. We know the drag force equation is negative b times velocity. So let's create a computational model based on that, weight force and drag. Similar initial conditions, but for the value of b, I guessed and checked with my data in the computational model until I found a output value similar to my collected final position value, in which I found the value of 0.002 to be the appropriate b for my computational model. Using the same time, I only changed the net force equation to also include the drag force based on the formula I discussed earlier, updated the object's velocity and the object's position, and ran the model. Again, you can look at my code if you would like to run the computational models yourself. And here is the position versus time graph for both computational models and my observed model. The computational model with drag was slightly better with the curve, but also it does not follow my observed data perfectly, which we can attribute to my own error within the experiment, the fact that the ball did not fall straight down. There could not have been, maybe there wasn't enough drag. But we can see there's a difference between the computation model with drag and without drag. So what does this all mean? Which model predicts a terminal velocity? Well, we know terminal velocity is when the net force is 0 and the ball moves with a constant velocity, which is when the drag force is equal to the weight force, the force of weight exerted by Earth. We can see from the initial computation model where there was no drag, the velocity does not change at all, which we would attribute to a constant force, which is the weight force being applied. However, with the second one where we included drag, we can see the velocity does change, and this is when the drag force becomes equal to the weight force. We can see a slight shift in the velocity. So the second computation model that includes drag predicts a terminal velocity. which adheres to physics principles. Now, what if there was an initial downward velocity? Well, this doesn't change terminal velocity at all because we know that the terminal velocity is dependent upon mass. Therefore, they're including a different initial velocity value does not change the speed at which the speed of an object's, the magnitude of an object's terminal velocity. So the only difference we can see here is the initial velocity, in which I use initial velocity of -1 in the y direction. But the slope is similar, therefore terminal velocity is achieved in both. In conclusion, we can tell that it is important to include the drag force when predicting the motion of a falling object, because objects in real time do encounter a drag force, and it is inappropriate to not include it in your calculations and your predictions.